Hello, everybody. Um, yes, today we're talking about leader election, which is it's a very, very broad topic, and it's very useful across distributed systems, not just databases generally, but you can use it for processes. So maybe like PM2, for example, where you can spin up your Node.js processes in cluster mode, and then you have to maybe elect the leader if you want to handle writes differently from reads, or you want to synchronize your systems. But today I'll narrow it down to just what we covered in the chapter, and then maybe some other useful links we can have to make the concept a little bit more clearer. My name is Pascal, Obba to keep it short. I am a software engineer at Cloudflare. Yeah, basically that's it. We are like a proxy that sits in between our client servers to like provide DNS, like WAF detection, DDoS mitigation, all of that. So that's what I do. So to get started, leader election is the process where nodes in a distributed network coordinate to give a specific node the role of a leader. Basically, what this means is we have a distributed network. You can think of this as process level. So you have a particular metal with 20 processes on them, or you have different like actual machines. So this is not like on a single machine, but you have a data center with many servers on them, or you have many data centers with servers distributed in different regions of the world. And you want to coordinate these nodes to be able to choose a particular node to be the leader of the network input. What that can look like is you can have, so let's use processes, for example, but you can imagine them as nodes in a particular data center or across data centers. And we have three processes now. And we are saying, oh, how do we want this election to go? So process P1 can say, oh, basically depends on how your data center is structured. Sometimes if it's in like a P2P Bitcoin network, you can have beacon nodes. What it means is when a node starts up, it's like it has a list of all the nodes or peers you should connect to at the beginning, because it doesn't yet have information about what's around it. Some other type of clusters provide some sort of DNS where you can query to like see other nodes on the network, and think of it like ARP where you do address resolution. You can query the particular host, or there's a process that manages like memberships, and then it can tell you these are all the nodes on the system. So let's say P1 is aware of P2 and P3 by DNS, and all the nodes are aware of themselves. Okay. So P1 also tells P3, please vote for me. I want to be the leader. P2 tells P1, vote for me. P2 tells P3, vote for me. P3 tells P2, vote for me. P3 tells P1, vote for me. Okay. So I think here we can see that this algorithm has a big notation of O of n square, because every node communicates with every node in the network. This is why specific algorithms have been designed with different trade-offs. So basically, if you look at what we just did, every node had to speak to every node. And imagine that across 300,000 servers, for example, or 300 servers, not to make it to like big, but that would be unbearable. It's like sending a broadcast from every node. So process one tells every process, please vote for me. Process two tells every process, please vote for me. So every time the election wants to happen, it's going to be a lot of chatter in the network. All these things come at a cost. So you have like bandwidth usage and then network issues, because every node is trying to communicate with every node. So different algorithms have been designed to say, how do we manage this situation, or how do we make it faster? How do we compromise, and how do we compromise? Some algorithms can say, should we ask only a few nodes on the network to engage in voting? So basically, instead of asking all 300 nodes, is it possible we ask only 5 nodes in the network? This will have its own issues as well. When will it be useful? How do we do this? Some other algorithms can say, should we allow multiple leaders on the network, which is a transient state. So you can think of it like how transactions work in a database. So like you have 2 transactions, and then maybe Postgres, for example, does something like multi-version concurrency control, where every process running its own transaction is isolated. So it thinks that is how the state of the database is. And then at the end, depending on the isolation level, it tries to say, okay, this will be the final state. So some algorithms can say we can have 10 leaders at a time, but eventually they'll end up picking one. But just so that we don't slow down the progress of our network, let us allow this transient state, even if it's not final. So depending on how you want to implement it, you can have this, some algorithms do this with like Paxos, multi-Paxos, which we won't go into because leader election is basically some form of consensus algorithm, but we are covering consensus algorithms in some chapters down below. But just to put it out there. Yeah. Okay, so why do we want to do leader election? Like, what is the use case for it? First thing is to achieve ordering and synchronization, and this is very important. So imagine you have a fintech app. So let's just do something very basic, something like maybe Paystack or something simple where you have maybe 10,000 naira in your balance and you want to spend money. So let's say we have 4 processes in this instance, and we spend 5,000, it goes to the first process. We spend 5,000 again, it goes to the second process. If we want to spend another 5,000, ideally at this point, we should have 0 in our balance because we've spent 5,000 twice, which is 10,000. But if we don't order it properly, if we don't synchronize the processes, process C might not know that 2 processes are already handling 2 in-flight transactions. So we might end up spending 15,000 more than what we have because we haven't handled the other 2 transactions yet from different processes. So if you imagine where we have just one process, which is the master, and it says every write to the DB will go to this particular service. So all the 5,000s will go to that particular, all the debits that are meant to happen for that user will go to the same process, which makes it ordered. So if I do the first one, the second one, by the third one, I already know that this user's balance is empty or the user doesn't have as much. So it makes sense for ordering. And it also solves the issue of replication. So every other node can handle reads. So how much is my balance? Every process can return that. But I want to spend from this balance. Only one process will handle it. I've done like lots of these in the past, and it just helps with like ease of work because you don't have to synchronize every time to say, oh, are any other in-flight transactions happening? Another thing it helps with is synchronization. So if your network crashes, I think 2 sessions ago, Bakary spoke about maybe right ahead login and like how the database is like managed states with logs. Daniel, I think I want to manage states with logs. Then we can have one process that is in charge of ensuring that we bring everything in the network up to speed. So this will help. Imagine if we had 20 processes trying to bring the network back up when we like restart, for example. That would be difficult to manage. So basically, with leader election, there's one particular node in charge of handling everything that has to do with bringing back our network after maybe a fault or a crash. The example I gave here is a Postgres instance handling writes and the replicas handling reads, which I think many people would have done. Is like a leader-follower model where you are having a lot of hits in on your service, and you're like, okay, how do I scale it up? But you don't want to have a multi-master situation where you have multiple processes handling writes. So the easiest way to scale up would be every particular replica can handle reads, the master node or the leader node handles the writes. And then there's a form of synchronization that happens from the replicas to say, oh, what's the latest state? And they all get updated. Okay, so that's a good reason to use leader election. So this is what I just spoke about, coordinate system reorganization after failures, where if for any reason our network is stuck or it's stale, we want somebody to be the source of truth. So a particular node should say, I'm in charge of this process. I have the replication logs and I'll handle reorganization instead of leaving it to happen concurrently with different processes. Reduce contention or locking. So this is so important as well. Like when you're working with distributed systems, I have had to like maybe work with Redis clusters, for example, where we have different caching processes, and I want to ensure that I am holding the lock so no other person can move. So for example, in the example I gave about debits, that would be a good way to solve it. So you have a distributed lock that the 4 processes share. So before you update somebody's balance, let's say Olalikon here, you have to ensure that you have the lock for Olalikon's like a record in database. So if you don't have that, you have to store. So other processes have to wait. And this can be problematic depending on how much the critical section is when you're handling the lock, when you're releasing the lock. With leader election, the only bound here is how fast can the leader go, but it's not going to be throttled by any other process. I think also leader election and locking is something that can be confusing. Like people use it like intermittently where they can put two of them against to say, oh, you can use leader election sometimes, you can use locking, but they are not the same thing basically. I don't want to point out the quick difference there. So yes, so firstly, locking can happen without the knowledge of other nodes on the network. Leader election is a coordinated effort. So if I hold a lock, no other node needs to know I hold the lock till another node wants to use it. So there's somebody's balance I want to update, I grab the lock. Other nodes, in a best case scenario, can process other people's transactions. They don't need to be stuck on that particular lock. Till I want to also update the record another process has or another node has, then I will now know, oh, this node A holds this lock, I have to wait for it. But with leader election, most of the time, many of the nodes need to know who the leader is so that they can send the right request to that particular node. So for example, if the node is A and node B gets a request to debit somebody's account, node B will have to forward the request to node A because it doesn't have the permissions to handle right requests. So leader election is more coordinated, more nodes need to be aware of what's happening in the network as opposed to locking, for example. Okay, locks need to be released to avoid starvation, while leaders can stay leaders for a lengthy period of time. This is very important as well. So if a lock is held for very long, depending on the type of system it is or what you're doing, then it might be a process where you have a deadlock or like you're not able to make any progress, especially if other processes need that lock to do something else. With leader elections, it is best when the leader is the leader for very long because you don't want to go through the whole hassle of, oh, the leader is dead, how do we do another election? So basically, if the leader stays leader for long enough, it's helpful because you're not stopping any other nodes from doing their work. But with locks, you need to ensure that you have like least timeouts and reasonable timeout sets to ensure that you don't hold the lock forever and stop other processes from using it. Okay, so when do we want to do the leader election? I think first thing is upon initialization of the network, which makes sense. So you start your like cluster, maybe your Node.js cluster or like your Golang service, whatever. And when the network starts up, you want to choose your leader then to say, okay, before we progress, who is handling rights and how do we know how to send the request to who the leader is? Now, that is also important to know because at startup, you want to also register your health checks to say, I want all the nodes to know how they can ensure that this leader is alive. For example, some of the issues you can have, which we should have spoken about in the last chapter, which is like failure detection, is how do I know if my leader is dead or how do I know if my leader is still alive? So you don't want stale data where the leader has actually moved on and you keep sending rights to an old leader because this particular client isn't aware of the updates happening. Secondly, when the leader crashes, so you can have hardware failures or kernel panics, and you want to be able to install or reinstate a new leader when a leader has gone down. If this doesn't happen, then you're going to have a lot of failed requests because you're sending requests to a process that doesn't exist anymore. Also, the network will be like throttled, like it can't make as much progress because you're going to have a backlog because your leader isn't alive anymore and you keep sending requests to it. Also, when a leader fails gracefully, like a crash is like hard failure. So you might not know about that. A graceful failure, it depends on the type of code structure you have or how you handle it, but it's also possible to gracefully hand over. So let's say you handle all the connections before you shut down and you're like, you can broadcast to the network to say, oh, I'm not leader anymore, I'm shutting down. And then a new election can take place as opposed to like a hard crash, for example. Then failed health checks because of poor bandwidth or less powerful hardware. So this is also very important because many times a node can be alive, but you can't reach it. So let's say you have a node that is fully connected. So let's say it's on Glo or it's on Ethel. And then you're trying to connect to this node, you're sending your health checks. The node is actually not dead, but because of how slow the networking is, or like the bandwidth isn't good enough, or let's say it's using some old version of the hardware, it can't respond to your health checks in time. So all the other nodes on the network think, oh, this node is dead, and you elect a new leader. And then you have two leaders, which can be a problem. So you want to carry out leader election when you're sure that, oh, I can't reach this node anymore. Which brings us like slightly to the actual failure detector, which we spoke about in the last chapter, I think. So basically what happens is it uses like a probabilistic model to handle failure detection. So if you try to ping a node and you can't reach it, you're like, okay, I will decrease this node's score by like a certain number. So you don't just declare the node dead. And then you try it multiple times. If it goes below a certain threshold, you can mark the node as dead. So this helps with like historic. So you know that, oh, this node keeps failing. So it's most likely dead. Or if the node fails once, but it has been doing well for a long time, you can give it more grace to say, well, maybe it's having a bad day. This node is actually still alive. Let's try more times. So it doesn't just try a health check and then if it doesn't work, it fails. It uses more like a probabilistic model to handle that. I mean, this is me simplifying what it does, but basically that's the concept of the fire failure detector. Okay. Some of the code bases I have used or seen do leader election, and the one I have used the most because I had to implement something like that. So I literally saw what Kubernetes was doing. So I think it was interesting to see, and it can help you like contextually understand what happens. But here, I just want it to, it's in Golang, so if you don't write it, I'm sorry, but it's not very complex. But you should mostly focus on the callbacks to say, on started leading. So this means when a leader wins the election, it notifies, you can run certain code in it to say, so run in this context runs the actual code in the main function or whatever you want it to do. So let's say this is a fintech app. It starts running the application on a particular port and starts accepting requests. On stop leading means, oh, I've lost this lease for whatever reason. And the way it works in Kubernetes is a little bit different. It's on a particular resource. So it can be in a particular namespace for a particular pod. And then that is like the lock in that sense. So anybody that tries to grab it will remain stuck, which is what you want to, which is what you desire here. So here on stop leading, you want to exit because you don't want a case where you have two leaders. So you log that, oh, you've lost the election or you're no longer the leader. And there's also a callback for if a new leader has been elected. Then there are many theories as well, which is very, 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 is more of an art than a science. So you have to gauge to say, oh, within my network, like for us, for example, we had to change some of the times. Maybe they are too slow or they are too fast, depending on the type of network you have. So 5 seconds can be slow depending on your networking. 1 second can be too fast. So you have to like play with times to see how often do I want to retry a failed leader election, or when should the deadline be renewed, or how long should you hold the lease before any election happens. So all those things are very dynamic. So the leader election, I think I linked the actual repo in the slides, but it will help to just read it. You might not use it, but to understand how it works in reality is very interesting. Console also does something similar. So you are able to hold a lease as well on a particular resource, and then a particular console application is the leader till it dies or it exits gracefully, and then it can hand off to somebody else. So yeah. Okay. Properties of leader election. Liveness. The election should eventually complete. I mean, it sounds very, very basic, but it's something you want to do. So you don't want to end up in a case where you keep voting forever. I mean, I don't want to shade any country, but sometimes the elections are going on for too long. Oh, who won? Nobody knows. So you want a situation where your network can make progress. In the end of the day, in reasonable time, the election should complete, which is a liveness property. In like distributed systems, there's liveness and safety. Liveness is basically saying something good is happening. Safety is like something bad shouldn't happen. That's like a good way to think of it. Okay. What else? there should be a leader most of the time also. You don't want a network where there is no leader, because that means things are not making progress. You're not processing your transactions. Depending on the type of network or system you have, if there is no leader most of the time, then your system is not making good progress. And then safety, at most one leader per time. So basically, in the end of the day, at least in your final state, you want to come to a place where there is only one leader in your network. If you have multiple leaders, it defeats the purpose, because as I said earlier, you want to synchronize your rights. So if you have two different leaders doing that, it's not going to be very possible. And I put ish there because it depends on your design. So sometimes, as I said, some algorithms want multiple leaders, and then eventually the multiple leaders can say, oh, who will be the leader here? And then they choose one. So, I mean, nothing here is hard and fast. With computer science, you can always do trade-offs to see, oh, can I have multiple leaders? And this brings us to like maybe how it works in AWS as well, or like just generally, you can also have multiple leaders in different regions, if that makes sense. So if you have like a very big network with some servers in China and then some are in like Nigeria, you don't want one leader like synchronizing everything, because it will become too much for it to handle. So basically, you can do multiple leaders sometimes. So that's why the issue is there. But basically, in the base concept of how to understand it, you want only one leader per team. Okay. Disadvantages of the leader follower model. It's not all shiny, sadly. The leader is the bottleneck or single point of failure, which is obvious. If your leader is dead, you can't process rights. So it's not as dynamic or flamboyant as a much more resilient network, which I'll go into a little bit of. We don't cover that in the chapter, but just to like hint at it. The network can only partially progress as fast as the leader. That must have good hardware, bandwidth, and throughput. So you almost need to give preferential treatment to what your leader nodes are doing. As I said, I use partially progress here because you can still process your reads, for example, but you can't process writes or anything that the leader is meant to handle if the leader is dead. So you will have to ensure like your leader is updated, maybe like kernel bugs, and like he has good hardware and like good throughput and bandwidth, because you can only go as fast as your leader. So yeah. Okay, partitioning a very large network into different replica sets, and each group has a leader helps reduce this bottleneck. This is just a random number, one leader for every 65 nodes, for example. So this is very helpful as well, because imagine if you have 300,000 nodes with one leader, like it's not possible. So no matter the spec you give it, 320 gig RAM or like petabytes of SSD, in the end of the day, the amount of load and request is going to be getting is going to be just so much for it to handle. Which is where the each comes in one leader, because you can partition or design your network in a way where you have specific nodes and there's one leader for a particular replica set. So for every 10 nodes, we choose a leader for every 10 nodes, and then we can synchronize around that. So that really helps the leader follower thing, because it doesn't really work well as you scale up. If you remember in the beginning, we spoke about how it's an O of n square algorithm, at least the first one we showed, which means that if you have 300,000 nodes, that's going to be ridiculous. You can imagine the number of messages that go through the network when an election wants to happen. So you don't want to be very resource intensive or like disruptive when you're having an election. Okay. So very few algorithms, 2-3 algorithms were covered in this particular chapter. So we'll just go through them. I think the first one is the Boolean algorithm. The Boolean algorithm is a simple algorithm in the sense that the way it works is processes get ranks assigned to them on startup. So imagine like all of us here are nodes, and immediately this network starts, Olalikon gets like 25, and Gochku gets 45, and I get 15. These are just random numbers. And all of us have this rank associated with us. So here's an example. Process Mike gets 25, process Janet gets 93. This means process Janet can bully Mike during the elections. So that's for the bully algorithm. Whoever has the higher rank has more stake in the network, basically, during an election. This is basically to like ensure that we don't spend all the time like going back and forth. So whoever has a higher rank can say, oh, don't worry, I will handle this election from here on. So let's assume that this is one particular node. It has a rank of 1. There's another node with a rank of 2, rank of 3, and rank of 4. So in this context, rank 4 is the leader because it has the highest rank. So let's say this network is already running, for example. So we already have a leader at this point. This is within the running phase, and then let's say it crashes. So rank 1 does its regular health checks. So as I said, when you're setting up your network, you register health checks to say, how do I know my network is healthy? What are the metrics I use to know that I can access my leader? It depends on the type of network you're doing. If you're having like a file system type of network, you're like, oh, can I write to this? Can I read from page cache? Whatever it is. And basically just says, are you there to rank 4? And it reaches out to the other nodes. So every ranked process reaches out to all the processes higher than it in rank. So since this is rank 1, it reaches out to all the other processes because it's the lowest. Okay, so are you there rank 3? Are you there rank 2? And rank 3 is like, oh yeah, I'm okay, I'm here. So keep quiet, basically. I'm here and I'll take it from here. So because rank 3 sees I am higher than rank 1, you don't need to worry. I will handle the election process from here. Rank 2 also says, I'll take it from here because rank 2 is higher than rank 1. So now we have rank 2, rank 3, and rank 4 because rank 1 isn't involved in the process anymore. So rank 2 reaches out to rank 4. Are you there? As I said, rank 4 is dead in this context, so nobody knows. Rank 2 reaches out to rank 3 as well because 3 is higher than 2. And rank 2 says, are you there? Rank 3 reaches out to rank 4 because the only thing higher than 3 on the network is 4. So rank 3 reaches out to rank 4 to say, are you there? As we said, rank 4 is dead, so rank 4 never replies. And rank 3 says, yes, I'll take it from here. So since rank 3 has nowhere to take it from because 4 never replies, 3 has won the election. And 3 says, oh, I'm the leader, I'm the leader, I'm the leader. So basically announced to all the nodes on the network that it is now the new leader of the election. Okay, so the first thing to note is with this particular algorithm, we can have a split brain situation. Split brain situation here means we can have multiple leaders. As I said, imagine a context where rank 4 is just like on Airtel, for example. So it's actually still alive and is there, but it can't respond to any of the requests. So by the time it's back, it's actually a leader, and rank 3 is a leader as well. Higher ranked nodes become bottlenecks. So as you can see in this particular network, the highest one that responded the most, which is rank 3, did most of the talking. So rank 1, for example, it was bullied early to say, keep quiet, your other nodes higher than you, so it will take it from there. But rank 3 was involved in all the phases, so with rank 1 and rank 2. So if rank 3 isn't high bandwidth, high throughput, like good hardware, it also slows down the network. So it gives a type of like preferential treatment to particular processes in the network. Okay, so some things that people do to also help will be to distribute host quality metrics and take them into consideration during elections. So for example, we eventually figured that rank 4 is on Airtel. So next time we're doing the voting, we don't just vote for rank 4, even if it's the highest ranked node. We put other metrics into it. What is your upload speed? What is your download speed? What's the RAM size? Are you using an SSD or a hard drive? Anything that you want to use to judge how good is my system performing, you put that into the metrics you use to make your election. So you don't just vote based on the highest rank, if that makes sense. So in this condition as well, you can see it's no longer O of n squared like I explained in the first one, because after the first level, some nodes are dropped off in the election process. So we reduce how much chatter we're getting in the network, which is very helpful for throughput. Okay, so an optimization that was done is next in line failover, which is very helpful. So the leader at the start of like when I become a leader, I propose who my next in line should be. Just think of it like a traditional like monarchy. So like, oh, my 3 sons will be next. So a leader proposes a fixed set of alternatives. This reduces the amount of chatter in the network and elections can happen faster. In the best case that the node that detects the leader's failure is the highest ranking node in the list of alternatives, then it becomes the leader right away. So imagine that the first son or however it's done, finds out that the father is dead. It just knows, oh, I'm the next leader. No election even takes place. So in the best case, the next in line failover happens very seamlessly because no election takes place. But in the worst case, a different node finds out and it just pings the next in line. So it's not as like it doesn't go back and forth the way the actual Boolean algorithm works. So the chatter is reduced. Let's see how that works. So we have rank 1, which is a process with rank of 1, rank 2, rank 3, and rank 4. And rank 1 says, are you there? In this case, rank 4 is still alive, or the process was still alive. And at the beginning of the network, he replies with his next in line. So it's like, I have 3 and 2. So here, rank 4 never replies. So what we do is, we already have this at initialization phase. So all these processes have 3 and 2 in memory or on disk or however they want to store the information. So once it doesn't reply, it just says, who is next in line? It doesn't need to say, oh, who are the people above me? So that reduces the number of messages sent in the network. So it looks for who is next in line. Are you there? And rank 3 says, yes, I'm there, I'll take it, I'm the leader. So this is just way more straightforward because we don't have all the issues of, like now, rank 1 and rank 2 never needed to communicate in this particular algorithm because rank 3 was the highest ranked next in line. And then it was able to just reach out to rank 3 and rank 3 just accepted leadership position. So it's way more straightforward. Okay. There's also another optimization that was done, which is called candidate ordinary optimization. This is almost like how it works in reality. So like nodes are split into 2 subsets, the candidates and the ordinary ones. So you have like we, the normal people, and you have like your electorate, you have people that want to run for office in quotes. So you have candidates that want to be elected. So if the leader dies, you just choose from the candidates who will be next. It's almost like next in line failover. But it also helps, as I said in the beginning, this is not open spare, for example. We don't need to reach out to all the nodes in the network to say, oh, I want to be leader. You already have a set of candidates and then you choose a leader from there. Okay, so the highest ranked alive candidate becomes the leader. Reduce chatter from multiple simultaneous elections. A tiebreaker variable X can be used to introduce no specific delays. Okay, this is also a weird thing because it can slow down your network. So you have to be very careful as to what this tiebreaker variable will be. But what this means is, imagine if we have 20 ordinary nodes realizing that the leader is dead and it's like, oh, candidate A should be the leader, candidate. So many people at once spam the network because they all realize a particular leader is dead. So what happens is they introduce some form of like delay to the nodes to ensure that an election has already started. So before other nodes try to like push for an election has happened. This also happens with like exponential backoff. If you think of it with like timeout. So try to make a request and then you get a 400 and then we're like, oh, don't make another request till X amount of time. It's just to solve the thundering head problem where we don't want all the nodes coming back to say, oh, the time is past now, I want to make a request. So you introduce some sort of man-made delay. It's not really network driven. You can use some certain metrics to choose what this delay will be. For example, what is the round trip time for my network? So if it's 100 milliseconds, you know that it takes 100 milliseconds for me to send a request and get a response. Then I will set it at like 120. So another node should have started the election at 120 milliseconds. So you don't just set it to random values like 1 second because it will make your network very slow. So you have to look at metrics to say, what is a good amount of time I can use to set a delay where an election should have happened, and I should be able to come back to the network and realize that I'm not like spamming with multiple simultaneous elections happening. Okay. Nodes with higher priorities have smaller delays. So if you have like a candidate node or a leader node, it's going to have a very small delay because it's much more useful in the network. A very ordinary node should have a higher delay so it doesn't like span the network, basically. Okay. There's the invitation algorithm as well. Okay, Dami, you can ask question.
Hi, sorry, I just wanted to understand something about the candidate and ordinary one.
Yes.
So if there's a variable to kind of like reduce like the multiple simultaneous elections happening, and we say the ordinary nodes have like this particular variable, right? Um, if a particular ordinary node has like a much, I don't know if lower means that it feels like there's a particular node that would always start elections before the other nodes. Is that how this would play out? If nodes have like different this called a tiebreaker variable. Yeah, unless
Yes.
I'm
So
missing how the algorithm works. Yeah.
that's a good question. Yes. So, but the only part you're missing is it depends on who finds out first. So
Oh,
other nodes of, yeah. So if I find out at 10 a.m. and my delay is 120 milliseconds, even somebody that has just a delay of 5 milliseconds, if he finds out at 10:03, then I will still be the one to initiate the election. So when other nodes find out that the leader is dead, is when they initiate the election. Does that make sense? So even nodes
yeah.
with very low delays can still be the ones to initiate because they found out earlier. What we're trying to avoid is, because we know ideally in a healthy network, it shouldn't get up to 3 minutes. Other nodes will find out in good amount of time. We want to introduce a very small delay to ensure many nodes are not spamming it. But I get what you mean. And in most of the cases, yes. But ideally, the node that finds out first, the specific delay should not be large enough that it never gets to elect anybody. But to introduce a very small delay to ensure that we don't have other nodes spamming it, if that makes sense.
Okay. Thank you.
Okay, so the imputation algorithm is interesting because it just from the jump defeats the purpose of the leader follower thing, where every process is a leader from the beginning. So when we join the network, I'm a leader, Dan is a leader, Haley is a leader, and we all have our groups in quotes. Every group leader contacts peers that don't belong to their groups. So, which means every group leader contacts every node on the network, because at the beginning, no node belongs to any nodes group. Okay. If the node contacted is a leader, the groups are merged. If it is not, it returns the ID of the leader, and then the leader is contacted. Okay. When the merge occurs, it doesn't matter which of the leaders stays the leader. Most times, it's the leader of the group with the most peers. Okay. I think we just look at how it works. So we start out with, as we said, every like node is its own leader, and then I propose to say, oh, do you want to join my group? And it's like, oh, sure. And then we merge to become a group. So this is a group of 2 nodes now. They have merged, and then one is the leader. So basically, whoever proposes for the other person to join the group will be the leader of the group, or whoever has more nodes. So if you think about it, if I have a replica set of like 50 nodes and I'm reaching out to a different group to say, join my group, even if it was the other group that reached out to me, for example, and it has just 2 nodes in the other group, it won't make sense for 50 nodes to go and join a group with 2 nodes. So it means all the 50 nodes will have to change who their leader is and then use the leader. So sometimes you have to also say which group has more nodes, because it will be easier on the network in terms of bandwidth, throughput, or number of messages being circular, like spread around, to say this smaller group should just change whoever their leader is because it's easier to do that. Okay. In this case, we have a different group with 2 other nodes, and they have their own leader as well. Leader 1 says leader reaches out to a different peer and a different group to say, join me. And group 2 is node 2 is like, oh, I'm not the leader, my leader is 4. So 1 reaches out to 4 to say, join me, and 4 is like, sure. And then we have a group with 4 of them in it. Now, what this solves in a way is that it reduces the data as well. For example, only leader 1 here is reaching out to other nodes or other peers. So we don't have like what we had in the beginning of the Bully algorithm before we did any optimizations to say, oh, what's your rank? And then reaches out to many more nodes. And then if you go to a different group, the group doesn't need to find other. So let's imagine we had 7 other nodes here. All it needs to do is to say, you just have one more hop. It just tells you who the leader is, and you reach out to the leader directly. And And when that happens, as I said, the merge happens based on who sent the request. So like one says, join me. So one will be the leader in the next one. It depends on the algorithm you use. It doesn't really matter. What matters is you should have one leader at the end when the merge is done. This is also, okay, no. So this isn't a ring issue. We have like the ring algorithm, which we'll go to. But this doesn't have so like the nodes here don't know a ring. Like in a ring topology, for example, you know who your predecessor is, who your successor is. In this case, they just know who their leader is. So it's like a logical structure. It only makes sense when you're like looking at the network to say, oh, who are the leaders of this particular group? And then many nodes have one leader, and then different nodes have a different leader. So it's a logical distribution, if that makes sense. But it's not like a ring-like topology in this sense. Yeah. Okay. So this is also like can also fall prey to the split brain situation as well. So it's not really grand, but it makes sense in the context that, I mean, and it's also like the same bottlenecks and fallbacks leader one has. If the leader is down, for example, here, things cannot really make progress because all the nodes point to their leader. So how do they choose the next leader? All of that. But ideally, if everything works, it is less messages because every group has somebody they just point to say, oh, you handle it, and then they merge in it. Okay, so this is the ring algorithm I was talking about, Haley, where all nodes in the network form a ring-like topology. When a failure is detected, every node contacts a successor and maintains a live node set from all the nodes that respond. Nodes that fail to respond are skipped. If the size of the network is large, maintaining a live set of these nodes isn't always space efficient, so optimizations can be done to just for the highest ranking node in this set. Okay, let's just look at how it works. So we have a process 1, we have a process 2, we have process 3, process 4, process 5, process 6. And they're all connected. Think of it like a linked list, basically. So like process 1 knows who is in front of it and who is behind it. Logically, it's not really how like it is cabled or how the data center is structured. It just knows when it starts up who its successor is. It can also be a rank thing, whoever is ahead of me and who is behind me. Think of something like that. Okay, so 6 is the leader now, and 6 is dead for whatever reason. 3 notices that 6 is dead, so it starts an election. The way the election works here is it creates a set. Just imagine a map in memory or a set, and it sends this set to the next to its successor. Every set you send it to adds its own number to it. So 4 says, oh, I'm alive. So now the set is 3 and 4. 5 says, oh, I'm alive. So the set is 3, 4, 5. 6 doesn't exist because it's dead. So we skip it. And then, so basically, it doesn't work in this diagram, but 5 is what reaches out to 1. So 6 is dead, we skip it. And then the request goes to 6's processor. So this is 1. So we have 3, 4, 5, 1 in the set. 2 also adds its ID to the set. And basically, the algorithm stops when it processes its number again. So when it comes back to 3, 3 already has 3 in it. So it knows that it has gone round. So basically, if I hand something out and it comes back to me, then everybody has touched it. So we look at 3, 4, 5, 2 here, and 3 is like, oh, 5 is the highest ranking one here. And then he elects 5 the leader. Now, this is one of the most space inefficient algorithms because imagine if you have 300,000, I like 300,000, but imagine if you have 300,000 nodes on the network. What this means is if one of them was 1 KB, for example, whatever that is, maybe 300 gigabytes of just node IDs in storage, or 299 because, I mean, one of them will be dead. So it's just a lot of storage to pass around the network because you're increasing the bandwidth you will need to just like do a basic leader election votes, and which other election algorithms they now have. So an optimization that has been done is to like calculate this on the fly, for example. So when it gets to 4, 4 just drops 3, if that makes sense. So 4 doesn't need to send 3, 4, 5. Like 4 already knows, oh, I'm the highest here. So 3 leaves these sets. When it gets to 5, 5 knows that it's higher than 4, so 4 leaves the sets. 5 is higher than 1, so 1 doesn't even enter the set. 2 just looks and sees 5, it doesn't enter the set. So 5 just gets to 3, which helps you manage space. So you don't have to do like everybody add your number and go around, whatever. So in the end of the day, also you need to also handle the edge case where, because how we knew we had gone around initially was if you see your number again. So you need to like handle that. But basically you have to make it space efficient because with the way it works now, it is not. Okay. So those are the algorithms that were covered in the chapter, but I want to just touch on, I think we have 10 more minutes briefly, because I think it will help contextualize, understand other types of systems that exist. Aside the leader follower model, you're like, what else can we have? And we can have P2P systems. With P2P systems, there is no bottleneck of a single leader. This means many nodes within the network can drive the network, which makes sense. But as I said, it depends on what you're trying to solve. So like a financial application type of thing where you want to like order your rights and ensure that everything is structured. You won't want to do something like this. But imagine something like BitTorrent or like a blockchain where somebody wants to download particular thing on BitTorrent, for example. You can have many peers feeding that particular node. You can have peers with the best bandwidth, or you want to do like a gossip algorithm to say, oh, Pascal, how can you communicate to Dami's computer, for example? Many nodes can come in to say, oh, I have good bandwidth, I can help here. It just makes things way more robust in that sense because you're not depending on one particular node. This is mostly for write-heavy networks like BitTorrent and blockchain, for example. So imagine like a blockchain where you only have one node and like it will be impossible for it to handle. So basically the way it works now, you can have like multiple nodes, depending on the type of blockchain you're doing. Some people have validator nodes to say, oh, I will help drive the network forward. So you have to handle the case where there is no leader in that sense. So many nodes can lead the network, which is a very robust solution, depending on your use case. Byzantine fault tolerance algorithms are needed as this kind of networks can have bad actors. Okay, so this is a very interesting thing because you need to know that with this type of network, it is not like conditioned to a particular amount of people. So for example, when you're starting your PM2 instance running 4 Node.js applications or processes, you know that you're running 4, like you're the one in charge of it. In a P2P system like BitTorrent, for example, anybody can join the network. In a blockchain network today I can spin up a node and join the network. So it is possible that I want to steal money or I want to do something bad. These P2P systems have to be more robust than the normal, like naive leader election algorithms we've seen to know that how do I ensure that bad actors don't bring down the network. So there are specific type of algorithms called BFT algorithms, real-time fault tolerance algorithms, which like solves the Byzantine generals problem. It's basically imagine like generals going to fights and all of them can send messengers to tell people what the strategy is. And imagine if you have bad messengers as part of the people, how do you like curb it? It's a long thing, but like there are a lot of papers that have been written. Okay, nice. I didn't know that. But yeah, so you have like total number of nodes where if we have the node number greater than or equal to, it's also 3 times the number of bad actor nodes plus 1 in this example, then we can manage this particular edge case. So if we have 5 bad actors, for example, we'll need 16 nodes, which means 11 other healthy actors to ensure that we have a network that goes. Yep, that's very correct. So Tendermint does this as well. PBFT in this case is practical Byzantine fault tolerance. I worked for Eva Labs for a while as well, so this was very interesting. I got to work on just a very little bit of it, but yes. Okay, he also does with dynamic or works with dynamic membership because nodes can join or leave the system as they like. Yes, so basically, you know how we like had rank 1, rank 2, rank 3, rank 4. It's just going to be way more harder to manage in a P2P system because rank 1 might not exist tomorrow. It's like, oh, I'm done seeding, I don't seed anymore, I don't have data, and then a new member can join in. So you need to do a lot of management because you need to know who your peers are. Gossip algorithms are used to disseminate information. This makes sense because in a blockchain network, for example, you can't send a message to all the nodes, like you end up staying there for weeks. So basically you need to have a concept of your peers and you gossip to your peers gossip to other peers. So this isn't like all of n squared I explained at the beginning. You just send the information to who your peers are, you figure out your peers maybe based on geographical location or proximity or like the beacon nodes. And then those peers communicate to other peers as well. So that's a good way to manage distribution. And then Paxos avoids split brains by utilizing quorums, epoch, and proposal numbers. Okay. So in chapter 14, this will be covered more, which is why I didn't go into it as much. But basically, with all the algorithms we covered today, all of them can fall to the split brain situation. I mean, you can try your best to like handle the edge cases, but we have like Paxos, multi-Paxos, rafts, which are like very strong consensus algorithms that help try their best to like manage split brains, for example. So they're like quorum numbers to say, if we have 10 nodes, 6 nodes must agree that this is who the leader is. And then with that, they assure that the majority of the network is moving forward. You have epochs as well, which handles the case where a dead node comes back. So if a dead node comes back as the leader, it's going to like show when it thought it was the leader last, for example. And you can say, oh, I thought I was the leader yesterday. And then they're like, oh, man, we've moved on from that. Your epoch is old, so update it. And then there are proposal numbers as well. So you have like a sequence counter to say, when did you propose? And O'Reilly is like, oh, I proposed yesterday. They're like, oh, that's old, update it. So just how to manage to ensure that bad peers don't go out, come back into the network, and then cause confusion. So in chapter 14, that will be covered more, but that is how better algorithms handle split brain situations. In conclusion, leader election can lead to very stable and reliable networks. Using a designated leader can help reduce coordination, overhead, and maintain simplicity. It also reduces the amount of messages that needs to be sent over the network. I think this is self-explanatory. With a leader, you don't need all the chatter in the network with like a PSPS system, for example. Once you have who your leader is, and it can be very robust. Like we have some systems where you have a leader for more than 20 or 30 days, and you're sure that you're not having any break in your like your networking. If you have bad networking, then it's just not worth it because you end up doing elections every time. But if you have a very stable network, it's going to be very worth it to do. Election rounds can be expensive, but if high quality nodes and systems are used, it shouldn't happen. It should happen infrequently, which is what I just said. So if you have like good networking, good hardware, you don't need to always elect a leader all the time. If it happens like once in X number of days, it's a good trade-off to do. Single leaders can become bottlenecks, and this can be used by partitioning, which is what we spoke about. So when your network becomes too large, you think about partitioning it to say, for every 10 nodes, elect a different leader so that your leader isn't like stuck, because no matter how much hardware you give it, it's just always the bottleneck because the number of nodes you have will keep increasing. So you need like other ways to ensure that other leaders can come on board, but you still maintain the core basics of the leader-follower model. All our goals discussed today can end up in the split brain problem, which is what I stated. So everything here isn't really managing or handling this situation properly. You can write extra codes like cover the edge cases, but ideally with the way they work at the moment, many of them will fall for the split brain problem, which is where Paxos and co like come. So consensus algorithms like Paxos, multi-Paxos, Raft algorithms are just used to get the network to make a decision. Example, elect the leader. So yeah, basically the difference between consensus algorithms and this leader election in quotes is consensus algorithms can do more than just elect the leader. Like leader election is a small part of consensus algorithms. Consensus algorithms can be used to decide on anything. You can say we want to decide on how much we should give a particular person, which is what like some, what are they called in blockchain now? There's some DAOs, for example, to say, oh, how do we make a decision? It's just all consensus. So it's much more dynamic than just electing a leader. So yeah, that was it basically. I hope it was helpful. If you have any questions, I can take them. But basically, that is what the chapter is about. Thank you.
Yeah, thanks a lot, Pascal. Yeah, it was a very nice presentation, and it was really helpful walking through, the algorithms with diagrams and, yeah, like we were saying before we started the call, like the book is quite dense, so it helps just seeing some code and diagrams. Yeah, so thanks.
No worries.
Does anyone have? Yeah. Are there any questions from anyone? Okay.
Okay.
Yeah.
Thank you very much, everyone. Yep.
Yeah.
I'm available on Discord as well. If you have any questions, that's fine. I can take them anytime. But yeah, thank you.
All right. All right. Thanks, everyone. Have a great day. Yeah.
Bye.
Bye.